In this video, we are going to look at everything that you need to know for Cambridge A's Level Mathematics 9709, Pure Mathematics 1, Functions. Let's start with quadratic functions, the parabola. Quadratic functions take on the form ax squared plus bx plus c, or ax plus p squared plus q. In the three-term quadratic, a is the coefficient of x squared, b is the coefficient of x, and c is the constant. A quadratic has to have a term with an exponent of 2. It does not have to have an x term or a constant, as long as it has a term with the highest exponent of 2. It is a quadratic. A affects the shape of the graph. If A is positive, the graph will look like a smiling face, but if A is negative, the graph will look like a frown. The domain of a graph considers all possible x values. The domain of a quadratic runs from negative to positive infinity. The range considers all possible y values. The range of a parabola depends on the value of a. If a is positive, the range runs from the y-coordinate of the turning point up to positive infinity. But if a is negative, the range runs from the y-coordinate of the turning point down to negative infinity. Now let's look at the turning point. The turning point takes on the value negative pq when the equation is in completed square form. I find that it is easier to work with quadratic functions when in completed square form because we can easily see the values of p and q, and we can find the x and y intercepts. In completed square form, we have an x term and a constant in a bracket squared and then a constant outside of the bracket. It does not matter what variables these values are given. It can be c and d, s and t, j and k. As long as the equation is in this format, it is completed square form. When completing the square, we can use the following formula. To find p, we use b over 2a, and to find q, we can use c minus ap squared. Let's look at some examples. Convert the following quadratic equations into completed square form and determine the coordinates of the turning points of the graph. Here we have y is equal to x squared minus 6x plus 8. Here our a value is 1. B is the coefficient of x, negative 6. And c is the constant 8. To find p, I can use b over 2a. So I can say p is equal to b, negative 6, over 2 multiplied by 1, which is simply 2. Negative 6 divided by 2 gives me negative 3. For q, I can say q is equal to c is 8 minus a, 1, multiplied by p squared, negative 3 squared. Now I have 8. Negative 3 squared is positive 9. So we have 8 minus 9, which is equal to negative 1. So in completed square form, a is 1. You don't have to write it down. So open our bracket. We have x plus p. P is negative 3. It becomes minus 3 squared minus 1. For the x-coordinate of the turning point, we use negative p. P is negative 3, so the x-coordinate is positive 3. And the y-coordinate is q, negative 1. Let's do another one. X squared minus 4x minus 8. Let's find our value of p. P is equal to b, negative 4, over 2 multiplied by 1, which is 2. Negative 4 divided by 2 gives us negative 2. To find q, we say c, which in this case is negative 8, minus a, which is 1, multiplied by p, negative 2, squared. Now I have negative 8 minus 4, which is equal to negative 12. So in completed square form, I can say y is equal to, a is 1. I don't need to write that down. So I can open my bracket. I have x plus p. P is negative 2, so it becomes minus 2. Close the bracket squared, plus q, which is minus 12. For the turning point, negative p, this becomes positive 2, and a y-coordinate of negative 12. Let's do another one. Y is equal to 2x squared minus 12x plus 13. In this case, I now have an a value of 2. So to find p, I can say b, negative 12, over 2 multiplied by a, which is 2. 2 multiplied by 2 is 4, so I get negative 12 divided by 4, which is equal to negative 3. Now I can find q. So q is equal to, c is 13, minus a, which is 2, multiplied by negative 3, our p value, squared. And I get 13 minus 2 multiplied by 9, which gives me 13 minus 18, which gives me a q value of negative 5. Now in completed square form, I can say y is equal to a, the coefficient of x squared, 2, open the bracket, x minus 3 squared plus q, which is negative 5. And the coordinates of the turning point, negative p becomes positive 3, negative 5. Let's do one more. In this case, the coefficient of the squared term, a, is 3. So I can say p is equal to b, negative 12, over 2 multiplied by 3, which gives me negative 12 over 6, which is equal to negative 2. To find q, I can say q is equal to, c is 3, minus a, which is 3, multiplied by p squared, negative 2 squared. And I get 3 minus 3 multiplied by 4, which is 3 minus 12, which gives me a q value of negative 9. So in completed square form, I have y is equal to a, 3, open a bracket, x plus p, p is negative 2, minus 2 squared, plus q is minus 9. For the turning point, the x-coordinate is negative p, p is negative 2, so this becomes positive 2. The y-coordinate is q, negative 9. In these examples, all of our a values have been positive, so they take on the shape of smiling faces, which means that their range goes from the value of q up to positive infinity. In an exam, you may get formats that have a minus sign in the bracket, or a constant and then a bracket. No matter which way the format is given, we always find completed square form like this. Do not change the sign of p inside the bracket. Now let's look at the intercepts of a parabola. Let's start with the y-intercept. The y-intercept touches the axis when x is 0. So to find the y-intercept, make x equal to 0 in the equation. The x-intercepts occur when y is 0. So to find the x-intercept, make the equation equal to 0 and solve for x. There are two ways that you can solve for x. You can either rearrange the equation in completed square form, making x the subject, or use the quadratic formula. To solve for x, you can factorize and then attempt to solve, but it is very rare that x-intercepts are whole numbers or fractions. And in many cases, you will have large values of a or large values in your quadratic. And factorizing can be very time consuming. So always use the quickest method. If you have completed square form, rearrange the equation. If you have a 3-term quadratic, use the quadratic formula. Let's look at some examples and find the x and y intercepts. Here we have y is equal to x minus 3 squared minus 1. To find the y-intercept, we make x 0. So now we have y is equal to 0 minus 3 squared minus 1. 0 minus 3 is negative 3. Square, we get 9 minus 1, which gives us a y-intercept at 0, 8. To find the x-intercept, make y 0. We have 0 is equal to x minus 3 squared minus 1. To solve for x, we want the bracket by itself. So let's move negative 1 to the left. We get 1 is equal to x minus 3 in the bracket squared. To get the bracket by itself, we need to square root, which means we square root the left side as well. When working with parabolas, we need to consider the positive and negative root. So in this case, the square root of 1 is positive or negative 1. On the right, the square and the root will cancel out, and we're left with x minus 3. To find x, let's move negative 3 to the left. I have positive or negative 1 plus 3 is equal to x. 1 plus 3 gives me 4, which means that x could be 4. Negative 1 plus 3 gives me 2, which means that x could be equal to 2. These are x-intercepts. Let's do another one. Here we have y is equal to x squared minus 4x minus 8. Let's find the y-intercept. We can say y. Let's make x 0. We have 0 squared minus 4 multiplied by 0 minus 8. 0 with any exponent is still 0. So now we have 0. And when you multiply 0 by any value, your answer is 0. So we have 0 minus 8, which gives us a y-intercept at negative 8. To find the x-intercept, in this case, we have a 3-term quadratic. So we're going to use the quadratic formula. X is equal to negative b plus or minus b squared minus 4ac under a square root all over 2a. Now we can say x is equal to, b is negative 4, so negative b becomes positive 4, plus or minus b squared, negative 4 squared, minus 4, multiplied by a, which is 1, multiplied by c, negative 8, all under a root, all over 2 multiplied by 1, which is 2. Now I can use my calculator to find the value of the root. So let's open a bracket. Negative 4 squared minus 4 multiplied by 1 multiplied by negative 8 is equal to 48. Let's square root, and we get 4 square root 3. So now we can see that x is equal to 4 plus or minus 4 square root 3 over 2. To find the actual values of x, use your calculator. Let's start with a plus sign in the numerator. So I'm going to say 4 plus 4 root 3, divide this by 2, is equal to 2 plus 2 root 3. This is one of my x-intercepts, 2 plus 2 root 3. Now let's find x when we use the minus sign in the numerator. So I can say 4 minus 4 root 3 all over 2 is equal to 2 minus 2 root 3. So x is equal to 2 minus 2 square root 3. These are my two x-intercepts. Next, I want to look at the hyperbola. The hyperbola takes on the format y is equal to a over x plus p plus q, where a, p, and q are constants. Working with the Cartesian plane, the x and y axes, you know that it can be divided into 4 quadrants. The effect of a determines where the graph lies. If a is positive, the hyperbola will lie in quadrant 1 and quadrant 3. But if a is negative, the hyperbola will lie in quadrant 2 and quadrant 4. The hyperbola has 2 asymptotes. An asymptote shows us the values we cannot use, the values that make the equation invalid or undefined. In the equation, we have y is equal to a over x plus p. If x is equal to negative p, the fraction becomes a over negative p plus p, which means we get a over 0. A fraction with a denominator of 0 is undefined, and we cannot work with an undefined value. This means that x cannot be equal to negative p. If x is a coefficient, to find the asymptote, make the denominator of the fraction equal to 0 and solve for x. Your a value will never be 0. This means that this fraction will never be equal to 0, which means that y will never be equal to q. Now let's look at the domain and the range. The domain of a hyperbola runs from negative to positive infinity, but x cannot equal negative p. The range considers all values from negative to positive infinity, but y will not equal q. It is very important that you learn these basics because you will need them when working in this course. The hyperbola can take on different formats. It can be written as y is equal to a over x plus p plus q, or it can be written as y is equal to ax plus b over cx plus d. Please remember that if you have a fraction with an x term in your denominator, you are working with a hyperbola. In the exam, you may convert the format from one to the other, and there will be questions where you need to change from the format y is equal to a over x plus p plus q to y is equal to ax plus b over cx plus d. So let's look at how we do this. Convert the following equation into the form ax plus b over cx plus d. Here we have 1 over x plus 4 minus 2. In order to create one fraction, we need to give negative 2 a denominator. But specifically, we need to give this value the denominator of x plus 4. And the only way that we can do this without changing the value is to give it both a numerator and a denominator of x plus 4. So this means that in this case, we're going to have 1 over x plus 4 minus 2 multiplied by x plus 4 over x plus 4. Remember that when you have a fraction where you have the same value in the numerator and the denominator, the fraction is equal to 1. So now we have 1 minus, let's multiply 2 and x, we get 2x. Negative 2 multiplied by 4 gives us negative 8 all over the denominator of x plus 4. And this becomes negative 2x minus 7 over x plus 4. Let's do another one. 8 over x minus 8 plus 4. Again, let's multiply 4 by a fraction. So we can say 8 over x minus 8 plus 4 multiplied by x minus 8 over x minus 8. Now we get 8 plus 4x minus 32 all over x minus 8. Let's add like terms and we get 4x minus 24 over x minus 8. Now I'd like to move on to the transformation of functions. Let's start with reflection. When we reflect across a certain line, we call it the mirror line. Let's start with a reflection across the y-axis. The y-axis is our vertical axis. If a point or a graph sits on the left of the axis and we reflect across the y-axis, it will then sit on the right side. On the axes, x is negative on the left side and positive on the right side of the y-axis. So if we reflect across the y-axis, the value of every x coordinate will change signs, positive to negative or vice versa. So when reflecting across the y-axis, we change the sign of every x term in the equation. Now let's look at reflection across the x-axis. The x-axis is our horizontal axis. On the axis, y is positive above the x-axis and negative below it. So if we reflect across the x-axis, the point or graph will move from above the axis to below it or vice versa. So if y was positive, it will become negative. And if it was originally negative, it becomes positive. We know that when writing an equation, we can say y is equal to, as an example, ax plus b, or we can say f of x is equal to ax plus b. Both of these mean the same thing. So when reflecting across the x-axis, f of x becomes negative. So we multiply the whole equation by negative 1. Now let's look at stretch. I want to start with stretch parallel to the y-axis. When we stretch a graph parallel to the y-axis, it becomes taller. The degree that a graph is stretched is known as the scale factor. So if the height of a graph doubles, we have a scale factor of 2. If it becomes 3 times taller, we have a scale factor of 3, and so on. The y-coordinate of every point on the stretched graph will be multiplied by the scale factor of the y-coordinate of every point on the original graph. So if the original graph has a y-coordinate with a point of 2, and we have a scale factor of 3, 2 times 3 gives us 6. This will be the y-coordinate of the respective point on the new graph. We know that in an equation, y is f of x. So when transforming a graph, we multiply f of x by the scale factor. Let's call it k. Remember that this also works the other way around. If the height of a graph becomes shorter, then the scale factor is a fraction. So if the new graph is half the height of the original, then k has to be 1 over 2. Now let's look at stretch parallel to the x-axis. A graph can be stretched lengthways parallel to the x-axis. The degree is also known as the scale factor. This stretch only affects the x-coordinate, but when working with horizontal stretch, we divide by the scale factor in the equation. So if the graph is twice as wide as the original, then we divide x by 2. So the scale factor becomes 1 over 2. If the new graph is 3 times the width of the original, we divide by 3. So the scale factor becomes 1 over 3. Now we can move on to translation. Translation considers vertical or horizontal movement, up or down, or left or right. Let's start with the vertical shift. The vertical shift is movement up or down. To show the vertical shift in an equation, we add or subtract the number of units shifted to the constant q. Let's say that c is the number of units shifted. So if the graph moves upwards, we add c to the constant q. But if it shifts downwards, we subtract c from the constant q. Now let's look at the horizontal shift. This is movement left to right. This movement affects the x-coordinate of the graph. When the graph moves to the left, we add c to x. But if the graph moves to the right, we need to subtract c from x. Now let's look at a translation vector. A translation vector allows us to show the horizontal and vertical movement of a graph. Please make sure to learn this. You need this in your exam. P shows the horizontal shift. If P is positive, the graph shifts to the right. But if P is negative, the graph shifts to the left. Please be careful with this. It can become very, very confusing. As an example, let's say that we have x squared plus q. And we want to shift the graph 2 units to the right. That means that our translation vector becomes 2q. But in our equation, we use negative p. So this becomes x squared minus 2 plus q. As another example, let's say that I want to shift my graph 3 units to the left. My translation vector has p-value of negative 3q. But in my equation, I need to add 3. So this becomes x squared plus 3 plus q. Q shows the vertical shift. If Q is positive, the graph shifts upwards, but if Q is negative, the graph shifts downwards. When transforming a graph, we have to do it in a specific order. We start with reflection, either across the x-axis or across the y-axis. Then we look for the horizontal stretch, parallel to the x-axis. Then we look at the horizontal shift, also parallel to the x-axis. This is the p-value in our translation vector. After that, we look at the vertical stretch, parallel to the y-axis, and finally, the vertical shift, parallel to the y-axis. This is our q value. Now I want to move on to inverse functions. The inverse equation reflects across the line y is equal to x. This is our mirror line. If an exam question asks you to sketch an inverse function and include the mirror line, it is always the line y is equal to x. We know that when a graph reflects across the y-axis, the x-coordinates of the graph change sign, and this applies to the y-coordinates when reflecting across the x-axis. We are reflecting across the line y is equal to x. So to find points on an inverse graph, all you need to do is swap the coordinates of the original graph around. As an example, let's say that on the original graph, we have a point with coordinates 3, 4. This means that the respective point on the inverse graph will have coordinates 0.43. As another example, let's say we have point 2, -5 on the original graph. The respective point on the inverse graph will have an x-coordinate of -5 and a y-coordinate of 2. When showing the equation of an inverse graph, we give the f an exponent of a -1. It does not matter if you have f of x, g of x, h of x. To show the inverse, we put an exponent of -1 next to the letter. But please be careful. An exponent of -1 shows that we are working with an inverse function, but a small line that looks like an apostrophe means we are working with the derivative, and these are not the same thing. You will never see an inverse with an exponent of -2 or any other value. It will always be -1. To find the equation of an inverse function, you swap the x and y in the original function around and then make y the subject. Let's look at an example. Determine the inverse of the following function. F of x is equal to 2x plus 1. Let's start by making the subject y. So we can say y is equal to 2x plus 1. Now I swap my x and y variables. So I get x is equal to 2y plus 1. Now I need to make this y the subject of the equation. So let's move 1 to the left. I get x minus 1 is equal to 2y. Divide both sides by 2, and I get x minus 1 over 2 is equal to y. This is my equation for the inverse. So I can rewrite it as f, an exponent of -1, x is equal to x minus 1 over 2. Let's do another example. G of x is equal to x plus 2 squared minus 3. Let's make y the subject. So I have y is equal to the bracket x plus 2 squared minus 3. Now I can change my x and y variables around. X is equal to y plus 2 in a bracket squared minus 3. To make y the subject, I need to make the bracket the subject. So let's move -3 to the left. I get x plus 3 is equal to y plus 2 in a bracket squared. I need to get rid of the square, which means I need to square root. And what we do to one side, we do to the other. So we square root the side as well. Now we have x plus 3 under a square root. Keep in mind that when we are square rooting, we need to consider the positive and negative root. So we say positive or negative is equal to, on the right, the square and the root will cancel, and we get y plus 2. Now we can move 2 to the left. I'm going to get positive or negative x plus 3 under a square root minus 2 is equal to y. This is the equation for the inverse. I can write it as g, exponent of -1 x, is equal to positive or negative x plus 3 under a square root minus 2. Let's do one more. H of x is equal to 2 over x plus 1 plus 2. Let's make y the subject. Say y is equal to 2 over x plus 1 plus 2. Swap the variables around. X is equal to 2 over y plus 1 plus 2. To get y by itself, I need the fraction to be by itself. So let's move 2 to the left. I have x minus 2 is equal to 2 over y plus 1. To make y the subject, I need to move it out of the denominator of the fraction. So I'm going to multiply both sides by y plus 1. Let's put x minus 2 in a bracket, multiply by y plus 1 is equal to 2. To get y by itself, I now need this bracket by itself. So I need to divide both sides by x minus 2. And I get y plus 1 is equal to 2 over x minus 2. Now I can move this one to the right. I get y is equal to 2 over x minus 2 minus 1. For the original equation, we have h of x. So to write the equation for the inverse, I can say h to the negative 1 x is equal to 2 over x minus 2 minus 1. Now let's look at the domain and range of an inverse function. Just like the x and y coordinates of a graph swap around for an inverse function, so do the domain and the range. This means that the domain of the original graph will give us the range of the inverse, and the range of the original will give us the domain of the inverse. So as an example, let's say that f of x considers x values greater than 2. The inverse will consider y values greater than 2. Let's say that for the range of f of x, it considers y values smaller than 0. This means that the inverse will consider x values smaller than 0. This is very important. If you are given the domain of a function, this becomes the range of the inverse and vice versa. Now I want to look at types of functions. Let's start with one-to-one functions. In a one-to-one function, you will get one value of y for every value of x. As an example, let's look at y is equal to 3x plus 2. When x is 1, y is 5. When x is 2, y is 8. Straight lines and hyperbolas are examples of one-to-one functions, but we also get many-to-one functions. In a many-to-one function, you will get one value of y for more than one value of x. And as an example, we can look at y is equal to x squared. A parabola is an example of a many-to-one function. Here, if x is 2, y is 4. But if x is negative 2, y is still 4. So we have a y value of 4 for two values of x. In order to create an inverse function, we must use a one-to-one function. If an equation is a many-to-one function, it is not considered as a function and we cannot create an inverse. So in your exam, if a question asks you why an inverse function can or cannot be created, it is because it is not a one-to-one function. We know that a quadratic function can be a smiling face or a frowning face. Regardless of the shape, we get one value of y for every two values of x. So this is not a one-to-one function. But if we can limit the domain to the turning point or from the turning point onwards, we now have a one-to-one function. Let's put turning points on our parabolas. For the parabola on the left, if we limit the domain, we can consider values smaller than the turning point, and it will look like this, or values from the turning point onwards, and our function will look like this. This is now a one-to-one function, and we can do a similar thing on this side as well. Finally, I want to look at composite functions. Let's start with the basics. As an example, let's look at f of x is equal to 2x plus 3. X is the input value. We can substitute different values into x and find the respective values of y. So f of x is our output value. Let's look at an example. F of x is equal to 2x plus 3. Find f of 2. In this case, we need to substitute 2 into x and find the value of y. So I can say f of 2 is equal to, substitute 2 into x, I get 2 multiplied by 2 plus 3, which gives me 4 plus 3, which gives me 7. This is the value of y. Part B says find x if f of x is equal to 11. 11 is our y value. So we can say 11 is equal to 2x plus 3. Now we can solve for x. Subtract 3 from both sides. 11 minus 3 gives us 8 is equal to 2x. Divide both sides by 2 and we see that x is equal to 4. Now let's look at the equation of a composite function. And as an example, I'm going to use f g of x. The first letter shows us the output function. Here, f of x is the output. The second letter shows us the input function. So g of x is the input. To create a composite function, we substitute the equation of the input function into the x values of the output function. Let's look at an example. If f of x is equal to 2x plus 3 and g of x is equal to x squared minus a, determine part A, f g of x. Here, g of x is the input function. So we need to substitute the equation for g of x into the equation for f of x. So let's start with f of x. I can say f of x is equal to 2x plus 3. Now we substitute the equation of g of x into x. So I can say f g of x is equal to 2, open a bracket, the equation for g of x squared minus 4, close the bracket, plus 3. Now we expand, we get 2x squared minus 8 plus 3, which gives us the equation 2x squared minus 5. Part B wants us to determine g f of x. Now, f of x is our input function. So let's start with the equation for g of x, the output. We say g of x is equal to x squared minus 4. We need to substitute the equation of f of x into our x value. So we can say that g f of x is equal to, let's open a bracket, the equation for f of x, 2x plus 3, close the bracket, squared, minus 4. Now we can expand the brackets. We get 4x squared plus 12x plus 9 minus 4. Let's add like terms and we get 4x squared plus 12x plus 5. And this is the equation for g f of x. Finally, I'd like to look at the requirements for a composite function. For a composite function to exist, the range of the input must fall completely within the domain of the output function. This can be confusing at times, but just remember that the range of a function is all possible y values and the domain is all possible x values. So if we have the composite function f g of x, g of x is the input value and f of x is the output value. For the composite function f g of x to exist, the possible values of x in f of x must include the possible values of y for g of x. So in your exam, if your question asks why a composite function cannot be formed, we simply say the range of the input function must fall completely within the domain of the output function. Also remember that if a question tells you that something is a composite function, you do not need to check.